Lake Tahoe is a little more than 2 inches from reaching its full legal limit, and water is still flowing into it. And that's why officials are releasing so much water into the Truckee River.
Lake Tahoe has always been known for its crystal clear waters and almost untouched beauty. But something is changing beneath the surface. As water levels drop during a persistent dry cycle, divers are beginning to uncover unsettling things hidden for decades. What was once buried is slowly reappearing, turning routine underwater work into something far more disturbing. While the lake still looks calm and deep blue above, what lies below tells a very different story. Today, we uncover what's really happening. The lake bed that refuses to forget. Beneath Lake Tahoe's famous clarity, divers are encountering a reality most visitors would never expect. The lake may appear pure and undisturbed from the surface, but underwater cleanup operations reveal something far more unsettling. A long, layered accumulation of human presence that has quietly built up over decades. Early dives in Lake Tahoe reveal routine debris, bottles, cans, fishing lines, and lost gear, accumulating over years of tourism. Though small individually, they form a troubling pattern of long-term human impact underwater. Deeper areas reveal tires, bicycles, and corroded metal objects, showing decades of discarded waste preserved in cold conditions. And then comes the unsettling realization: the lake does not truly erase anything. Instead, it holds onto it. Lake Tahoe's cold depths slow decay dramatically. In these near-freezing conditions, biological breakdown is reduced to a crawl, allowing objects to remain suspended in a kind of environmental stasis. Time doesn't disappear underwater. It simply moves differently. That is why even more complex finds begin to appear. During documented recovery efforts and underwater surveys, divers have located older automobiles near abrupt drop-offs and former shoreline access points. These are areas where roads once ended suddenly at the water's edge before regulation and environmental protections were fully established. Many of the vehicles are believed to date back to the 1940s through 1970s, a period of rapid shoreline development around the Tahoe Basin. Some of these cars likely rolled in by accident. Others were almost certainly discarded intentionally during a time when environmental consequences were less understood or less cared about. At deeper levels where sunlight fades completely and sediment turns soft and unstable, these objects take on a different character entirely. They stop feeling like trash and start resembling archaeological remains. Paint layers still cling to metal surfaces. Door frames, dashboards, and structural outlines are still visible in some cases, preserved by cold water temperatures that hover around 4 degrees Celsius, 39 degrees Fahrenheit. It is not preservation in the traditional sense. It is suspension, a slowing of time caused by chemistry and temperature working together to freeze objects in place. But the lake is not only filled with accidental remnants of human activity. There are also documented submerged sites that are officially recorded as part of its underwater heritage. In places like Emerald Bay, wooden shipwrecks from the late 19th and early 20th centuries rest quietly on the lakebed. These wrecks are mapped, studied, and protected, offering a controlled glimpse into the region's early transport and tourism history. Still, what makes Lake Tahoe unusual is not just what is down there, it is how much of it remains intact and how long it stays visible. Unlike rivers that continuously flush material downstream, Tahoe's deep, stable water column allows objects to remain in place for decades without disappearing from the system. Each recovered item is not just debris, it is a timestamp, a frozen moment of human presence layered into the lake's history. And as divers continue moving through these zones, one pattern becomes harder to ignore. The deeper they go, the less the lake feels empty, and the more it feels like something has been quietly building beneath it all along. But what they are about to find next changes the context of everything they've seen so far, because the lake is not just holding objects. It may also be responding to what has been entering it all along, and that's where things start to get even more complicated. The pressure you can't see in clear water. From the surface, Lake Tahoe still looks like it belongs in a different world. The water is so clear it can feel untouched, almost too pure to be real. Scientifically, it is classified as an oligotrophic lake, meaning it naturally contains very low levels of nutrients like nitrogen and phosphorus. But that same condition is also what makes it extremely fragile. Because in a system like this, even the smallest change is enough to start a reaction. The sources of that change don't come from one place. They come from everywhere around it. Across the broader Tahoe Basin, a watershed spanning more than 500 square miles continuously drains into the lake. During storms and snowmelt, water runs off roads, parking lots, and residential areas in places like South Lake Tahoe, Tahoe City, and Incline Village. As it moves across these surfaces, it picks up fine particles, nitrogen compounds from vehicle emissions settled into dust, phosphorus from disturbed soil, and organic debris from landscaped areas. By the time that water reaches tributary streams feeding the lake, it is no longer just runoff. It has become a delivery system, and it doesn't stop there. Another layer of input comes from the atmosphere itself. Nitrogen oxides produced by vehicles and industrial activity can travel long distances before eventually settling directly onto the lake surface or surrounding terrain. This means nutrients are entering the system even without a visible pipe, drain, or discharge point. It is constant, quiet, and difficult to trace back to a single source. Historically, the problem was even more direct. Earlier shoreline developments relied heavily on septic systems before modern wastewater infrastructure was fully established around the basin. Over time, leakage from these systems contributed measurable nutrient loads to groundwater and nearshore waters. Even though major upgrades have significantly reduced this issue, the long-term impact remains embedded in the lake's environmental history. Today, newer pressures continue to add on top of that foundation. Residential fertilizer use, even when carefully applied, introduces additional nitrogen and phosphorus during irrigation or rainfall events. In most lakes, this kind of input would be absorbed without major consequences. But Tahoe is not most lakes. Here, there is almost no biological buffer. That is why even small nutrient increases begin to matter. Slight changes can stimulate algal and phytoplankton growth, especially in warmer nearshore zones where sunlight intensifies biological activity. It doesn't create sudden green water or dramatic visible blooms across the entire lake. Instead, it creates subtle shifts, slow changes in how light travels through the water. Over time, these shifts show up in clarity measurements like Secchi disk readings, which have recorded long-term variability since monitoring began in the late 1960s. There are periods of recovery, especially during low runoff years, but the overall pattern reflects increasing sensitivity rather than stability. Because in a lake this clear, clarity is not just a feature. It is a balance. And once that balance starts reacting to even the smallest input, the next force becomes even harder to control, because it doesn't dissolve into the water like nutrients do. It stays suspended, and that is exactly what begins to dominate the system next, when the lake stops being truly transparent. Unlike solid debris that sinks and stays in one place, the real threat to Lake Tahoe's clarity is far more subtle. It is not the objects you can recover with a dive team. It is what you cannot easily see at all. Fine sediment so small it stays suspended in the water, constantly interacting with light and slowly changing how deep the lake appears. The process starts far from the shoreline. Across the surrounding basin, steep granite slopes meet expanding human development. Roads cut through the landscape, and over time, they accumulate layers of dust, tire residue, oil particles, and loose material. During dry periods, all of this builds up silently on paved surfaces, but when storms arrive, that buildup is washed away almost instantly. Stormwater systems and tributaries like Trout Creek and the upper Truckee River then carry this material straight toward the lake. These waterways act less like natural streams during heavy runoff events and more like fast transport channels, delivering sediment directly into nearshore zones. Construction activity adds another layer of pressure. Even with modern regulations, disturbing soil on steep or fragile terrain creates short-term exposure. Once vegetation is removed, rainfall can easily dislodge fine particles, especially in a basin where erosion happens quickly and recovery is slow. Then there is wildfire. In recent years, burned areas around the Sierra Nevada have introduced a more unpredictable source of sediment. After intense fires, soil becomes water repellent. Instead of absorbing rainfall, the ground pushes water across the surface. As it moves, it collects ash, charred organic matter, and loosened mineral particles, sending them rapidly into streams after even moderate rain events. These post-fire runoff pulses can overwhelm the system in a short time, delivering concentrated sediment loads that temporarily reduce clarity in noticeable ways. Once these particles enter Lake Tahoe, they do not behave like heavier debris. They do not sink quickly. Fine silt and clay remain suspended, especially in cold, low-energy water conditions. Wind action and natural mixing keep them circulating in near-shore zones, where they directly interact with incoming sunlight. And that is where the real change begins. Instead of visible pollution, what forms is a thin, almost invisible layer that scatters light as it passes through the water column. This reduces how far light can penetrate, which is measured using Secchi disk readings, where a white disk is lowered until it disappears from view. Long-term monitoring by institutions such as the UC Davis Tahoe Environmental Research Center has recorded fluctuations in these readings since the late 1960s. While Lake Tahoe still ranks among the clearest large lakes in the world, the trend line shows variability and gradual decline from historic mid-century clarity levels. But the system is not responding to just one source. It is responding to many at once. Urban expansion increases impervious surfaces like roads, rooftops, and parking lots, which speed up runoff and reduce natural filtration. Snowmelt from the Sierra Nevada adds another pulse, shifting from slow seasonal release to more abrupt inflow events. Each of these processes increases how much sediment reaches the lake and how often it arrives in bursts instead of balance. And when these bursts overlap, something else begins to happen beneath the surface. Because sediment doesn't just reduce clarity, it changes how life behaves in the water itself. And that shift opens the door to something even more disruptive. The tiny invader that changed everything. In a lake as clear and tightly balanced as Tahoe, ecological disruption did not arrive loudly. It entered quietly, through something so small it was almost invisible at first. Back in the 1960s, a species of freshwater shrimp known as mysis was introduced into several western lake systems. The idea seemed harmless at the time. In fact, it was considered beneficial. These tiny organisms were expected to serve as an additional food source for fish, particularly kokanee salmon, and help strengthen the aquatic food web. But Lake Tahoe did not respond the way anyone expected. Instead of staying in accessible zones where fish could feed on them, mysis shrimp began migrating vertically through the water column. During the day, they settled into deeper, colder layers. At night, they moved upward. This behavior placed them in direct overlap with native zooplankton species that also depended on those same deepwater zones. And that is where the imbalance began. Native zooplankton populations, organisms like cladocerans and copepods, started to decline in key regions of the lake. These tiny grazers play a critical role in maintaining clarity because they consume phytoplankton and suspended organic material. When their numbers drop, biological control over algae weakens. The result was not immediate or dramatic. There were no sudden algal blooms spreading across the entire lake. Instead, the changes unfolded slowly, almost invisibly, through shifts in energy flow and food availability. Over time, the lake's internal structure began to reorganize. Plankton distribution patterns changed. Predator and prey layers in the water column became more separated, and with that separation came subtle but measurable effects on how light moved through the water. Researchers tracking Lake Tahoe since the late 1960s have documented these long-term changes in water clarity and biological activity. What they found was not collapse, but disruption, small adjustments that accumulated over decades. The mysis shrimp also created an alternative energy pathway deeper in the lake. Instead of becoming a simple food source for nearshore fish, they established themselves in colder depths, recycling organic material in areas that receive little sunlight. This effectively split the lake's energy system into two layers, one near the surface and another hidden far below. And once that split formed, it became difficult to reverse. Other invasive species followed, including aquatic plants like Eurasian water milfoil, which spread through boat traffic and established dense patches in shallow coves. These plants trap sediment, alter flow patterns, and change habitat structure in near-shore zones. But perhaps the most persistent factor is not the organisms themselves. It is how they arrive. Human recreation, especially boating, continues to act as a transport system for microscopic life, moving species from one body of water to another despite inspection programs and cleaning protocols. Because once an ecosystem pathway is opened, it rarely closes cleanly again. And as these biological shifts settle deeper into the system, the next layer of pressure begins to emerge, not from living organisms alone, but from a changing climate that is reshaping the entire environment from above. When the climate starts rewriting the lake. High in the Sierra Nevada, Lake Tahoe is no longer responding to a stable rhythm. What once followed predictable seasonal cycles is now being reshaped by gradual but persistent climate shifts. Changes measured not in dramatic storms alone, but in small temperature increases, altered snowfall patterns, and subtle timing disruptions that compound over years. The first major shift begins with snow. For decades, the Sierra Nevada snowpack acted like a natural storage system for the lake. Winter snowfall accumulated at high elevations, then melted slowly through spring and early summer. This steady release fed tributaries like the Upper Truckee River and Trout Creek, maintaining relatively balanced inflow throughout the year. But warming trends across the western United States have disrupted that system. Snow is still falling, but it is melting earlier. Instead of long, sustained meltwater input, the lake now receives shorter, more intense pulses of runoff. Water arrives quickly, often earlier in the year, followed by extended dry periods where inflow is reduced. This shift does not just affect water levels. It changes the internal timing of the entire lake system, from temperature layers to nutrient distribution. And that is only the beginning. Lake Tahoe is a demictic lake, meaning it naturally mixes twice a year, once in the spring and once in the fall. During these turnover periods, oxygen and nutrients are redistributed throughout the water column. But as air temperatures rise, the duration and strength of these mixing cycles are beginning to shift. Warmer surface waters stay stratified for longer periods, forming a more stable layer on top of colder deep water. This extended stratification reduces vertical mixing, which means less oxygen is transported to deeper zones and fewer nutrients are cycled upward. At first, these changes seem minor, but in a low-nutrient system like Tahoe, minor changes matter more than anywhere else. Microbial activity in deeper layers becomes more sensitive. Organic material breaks down differently. Particles remain suspended longer. Even small changes in oxygen concentration can alter how efficiently the lake processes natural organic matter. Over time, these internal shifts influence everything from water clarity to biological productivity. Then comes a more visible stressor: wildfire. In recent decades, wildfire activity across the Sierra Nevada has increased in both frequency and intensity. Hotter summers, earlier snowmelt, and longer dry seasons have created conditions where fires spread more easily and burn more aggressively. Events like the 2021 Culdor Fire, which impacted areas within the Tahoe Basin, show how fire is no longer distant from the lake. It is part of its immediate environment. When these fires burn, they do more than destroy forests. They inject massive amounts of ash, fine particulate matter, and dissolved organic carbon into the surrounding watershed and atmosphere. Some of these particles settle directly onto the lake's surface. Others are carried into tributaries during post-fire rainfall events. The result is a pulse of chemical and physical input that temporarily alters water quality. Ash contains nutrients like nitrogen and phosphorus. In a nutrient-limited system, this can briefly stimulate biological activity. At the same time, fine carbon particles and organic compounds absorb and scatter light differently, affecting how deep sunlight can penetrate the water. These are not permanent changes on their own, but they add volatility to a system that was once defined by stability. And then there is the interaction layer, where climate change and human development begin to amplify each other. Warmer temperatures increase evaporation, while changing rainfall patterns alter runoff timing into the basin. Urban growth adds impervious surfaces, speeding runoff and reducing filtration, so storms carry more material more quickly. Lake Tahoe is shifting from balance to extremes, with wider variability in conditions and increasingly unpredictable environmental transitions. And that is what makes this phase so critical. Because the lake is no longer simply reacting to one stressor at a time. It is responding to all of them at once. Climate, wildfire, development, runoff, biological change. They are no longer separate categories. They are overlapping forces, each amplifying the others, each reshaping how water moves, how particles behave, and how light travels through the system. And beneath all of it, the lake is slowly shifting toward a new kind of baseline, one that is less about clarity and stability and more about constant fluctuation. From the surface, it may still look like the same deep blue lake visitors have always known. But beneath that image, the system is no longer behaving like it used to. And as these pressures continue to build without pause, one question becomes unavoidable. How long can a lake this sensitive keep adapting before the changes stop being temporary and start becoming permanent? Thanks for watching. If you enjoyed the video, don't forget to like, subscribe, and check out more content for similar stories and updates. See you in the next one.